Here we'd like to predict what motion maps will look like for several balls that are released from rest. One of them is going to be resting on a level surface. So that's just going to look like this. There's our marble. We're also going to have a small angle ramp for it to roll down. And finally, we want a ramp that is so steep that it's actually a 90-degree ramp. So how do we measure the angles of our ramps? We just measure them with the horizontal here. So that makes this one a 90-degree ramp. This one could be a small angle, like 15 degrees maybe, or 30 degrees. And this one would be a 0-degree ramp. Now we also want to show what our x-axis is, because that's going to be important in our motion graphs. So let's go ahead and define that. Like I did in my previous video, I'm going to let the x-axis be aligned with the surface of the ramp. That's common for these types of problems. And I'll let the positive x direction be down the ramp in all cases. And similar to what I had done in my previous video, I'm going to let the 0 of the x-axis be the starting point for the ball. We have to define what the x-axis is in order to draw the motion maps. Now let's also state that each of these balls is going to be released with a velocity of 0. That means they're going to be at rest. Perhaps someone is holding them in their hand before they let go. And that gives us a starting point for our velocity graphs. Now go ahead and predict what you think the motion graphs will look like for these situations. Draw the x versus t. That's position versus time. And let's also draw the velocity versus time. You can try the acceleration versus time if you wish as well. And I'll give my answers to it shortly. Okay, so one of the things we're going to want to do here is find starting points for our graphs. So for the position versus time graphs, notice that our ball is at the 0 of the x-axis. And that is going to be the start of the clock, time 0. So at t equals 0, x equals 0. That means each of these graphs actually needs to start with a dot at the origin, and we're just going to go from there. We also notice that the velocity is 0 for all the balls at time 0. So let's start each of our graphs here. Okay. What should our position versus time graph look like for this case? You release the ball on level ground and it doesn't go anywhere. If its position doesn't change with time, then it should remain 0 for the rest of the time. And so we just want to connect these points, and that's going to be the graph for that ramp. This object remains at rest. How do you tell? Its position doesn't change. What should its velocity do? Should its velocity change as it sits there? No. Its velocity will remain 0 throughout time as well. Now let's take a look at the small angle ramp. I showed in my previous video what a graph of a ball on a ramp would look like. It would be a parabolic curve for the position versus time. When it comes to the velocity versus time graph, we'll just see a straight line linear change. But now the question becomes, how do you think the motion on this ramp would compare to the free fall ramp? So what'll happen is we'll actually get a steeper increase. The velocity will increase more rapidly. And then when it comes to our parabola, it's going to be steeper. It's going to reach the end of the ramp at a quicker rate. Now we should also draw the acceleration. Now, just like the velocity graph is the slope of the position graph, the acceleration is going to be the slope of the velocity graph. That's why we stack them in this order. So when it comes to this guy, there is no acceleration on that ramp. It's just 0. These are the graphs of an object that remains at rest throughout time. There'd be no change in position, no velocity, and no acceleration. Here we see that this graph actually does have a non-zero slope. And notice that it's a positive slope. So we want our acceleration to be a positive, consistent value. So there is acceleration here. Whereas we had no acceleration in this case. Here, our slope is steeper for the velocity graph, so we want a higher value for that acceleration graph. And there will definitely be acceleration in this case. Not just acceleration, but more acceleration than there was in the low-angled ramp.